Hello. VHDL is a procedural language which also allows descriptions of concurrent behavior, and most problems that are to do with programming can be sorted out just from prior knowledge of another language. So normally you can have a good guess at what the syntax may be, and it won't take you long to come up with a result that works. However, there are certain situations where it seems to defy any kind of reason or intuition, and what this video will do is describe 3 such situations. So it's not even the case of reading the LRM, because it won't be obvious where to look in order to resolve these problems. The examples we are going to look at have not been contrived. They're just simplified examples of problems that our customers had. So hopefully you're going to find these useful. So here's the first one. We've simplified it to show just one architecture of an entity here. And we've got a declaration of this signal S1, which is an 11-bit standard logic vector. And we set the left-handmost bit, index 10, to the value 0 as a concurrent statement. Notice it's outside of a process. And we have a process here, so as you probably know, a process is just one giant concurrent statement. So any assignment we make inside of a process generates one driver for a signal. So here we've got a for loop, and we're iterating around this for loop a known number of times. We're putting literal numbers in here, so 9 down to 0. We know at compilation and elaboration what those values are, because we've literally typed them in. And we're setting each bit of the vector from 9 down to 0 to the value 1 with a gap of 100 nanoseconds between each, and then we're aborting the simulation. So when we run simulation, we might be surprised to see a waveform like this. So you notice here that S10 is always uninitialized. So you can see these here starting from the index 9 times 0 and gaps of 100 nanoseconds. Each lower bit becomes a 1 eventually. But S10 never changes, and we might look at that and go, well, how come? And it's not immediately obvious why. So the reason for this is because of the way for loops are elaborated. So a for loop here inside this process is dynamically elaborated. So what that means is only at runtime, when we actually execute this process, do we actually unroll this loop and see what it does. So in the meantime then, what the tool doesn't know is, do we need to drive every bit of the vector S1? So this is not a decision a tool vendor makes. This is actually in the language reference manual. This is the defined behavior. So the only sensible thing to do will be to create drivers for every element of S1 and make them a U initially. So what we've got here is a driver for every index 9 down to 0 of this vector S1, as we can see gained from this for loop. Those values 9 down to 0 will not surprisingly have the value U at the beginning of simulation, and every 100 nanoseconds each bit will become a 1. However, we've also here created a driver for index 10. So inside of this process, remember, each assignment in the process creates a driver. We have one driver for S1 index 10 inside of that process, and we have one here which is setting it to 0. So if we drive onto the same piece of wire a U and a 0, the U uninitialized will always win. So why this might not be obvious to us is because we've got fixed numbers here. Why can't the tool just work this out? And the reason is because the LRM states that for loops are only elaborated at runtime when they need to be. So what's the answer? Well, we could just move this inside the process. That will solve our problems. So if I were to run the simulation now, that would solve our problems. Now, what will be interesting, however, is, if what I've said is correct, then what we should be able to do is change this from a for loop. So let's comment out this for loop now. We'd also need to change this assignment to an aggregate here. We're just going to assign to a slice. So I'm going to set every element to a 1 in that slice. So let's save that and then run again. And we see now that S10 always has the value 0, because we no longer create a driver for it for bit 10 inside of this, because there is no for loop there anymore. So elaboration takes place at the very beginning of simulation, and it's understood that this process here will not create a driver, does not need to create a driver for S1 index 10, and this concurrent statement makes the value 0, so that's what we expect to see in the waveform. Okay, so the key takeaway from that is for loops are elaborated dynamically, i.e. when they're executed. So any problems that are built in there from bad coding, you're only going to find out at runtime. There is no check on these during the elaboration at the beginning of simulation. The next problem we'll talk about is a for generate loop. This is not to be confused with the for loop that we saw previously. A for loop is inside of sequential code. That means inside of a process or a function or any other subprogram. For generate is a concurrent statement, so it exists outside of a process, and what it does is allow us to conditionally do things like make signal assignments or instantiation of components or definitions of processes. So it's a way of conditionally including code at elaboration, and inside of a for generate loop we have concurrent statements. So what we have inside of this loop, we're iterating around for I in 1 down to 0, and on each iteration what we're doing is if a G1, which is a generic, has the value 1, we're generating this assignment. Field 2 gets assigned true. And as you can see from here, there's no definition of what field 2 actually is. So if we actually instance this entity called test with the value of generic G1 1, we're expecting to see some kind of compiler error here. So here's the instance G1 mapping to the first thing in the generic map list here, which is the number 1. So let's try and compile this. So as expected, we're getting a field 2 not declared error. So what we may think, and the purpose of this part of the presentation, is if we change this number then to something other than 1, so 0, we're no longer going to generate this assignment now. So we're expecting to hide that compilation error, we might think. But it's still there, even with that generic G1 having the value 0. So what that means is this condition is not true. Therefore, I shouldn't generate this statement, therefore I shouldn't get the compiler error. The reason we still see this error is due to how and when the generate statements are elaborated. Inside of a generate statement, it's replaced by block statements which are duplicated 0 or more times. So if we've got a loop like this, we're going to duplicate this code inside of it here 0 or more times. We do not know that, even though we've got fixed numbers in here, we don't know that at compile time. But at elaboration, when we unroll this, we elaborate this code 1 down to 0 times, and we don't yet know whether we're going to have to generate it or not based upon these if statements. So the outer loop is generated first, and subsequently we go and see if we need to generate the code or not. But we do not know that at the time. So up front, we do not know whether field 2, this assignment, is actually needed or not. And that's the reason for the error, because it is possible that would need that assignment to be generated, and therefore we would need a field 2 to be declared. So just changing the value of G1, the generic, to something other than this, making this if statement false, is not sufficient to hide that elaboration error. So to summarize, the reason for the problem is because these blocks in here, so this is a code block, this will get generated 0 or more times based upon how many times this for loop is elaborated, and the outer loop, the indices on the outside, are elaborated before the block code blocks in it, so we don't yet know at that point whether we need to generate this assignment or not, so you get an error. The third and final problem we're going to talk about is static cases. So almost everybody who's ever coded VHDL would have come across this, and I've yet to see a concise and clear description of what is actually meant by a static case in VHDL. So in this example, what we have is all design units inside the same file. So as you probably know, VHDL doesn't care about files, all it cares about is design units. So it doesn't matter if you have every design unit in one single file or you have it in multiple files. The most flexible and reusable thing to do is have each design unit in a separate file. So you notice why we need these library declarations here, because that library declaration highlighted only applies to the primary design unit following it, so it's not visible for the whole file. So if I want to define an entity as well in this file, I need the same, in some cases the same library declarations again, because they only apply to the primary design unit that follows it. The architecture doesn't need such library declarations because it's a secondary design unit, so it gets its library declarations from its primary, which will be this entity that we've just defined here. Anyway, that's not the point of this description. We have down here the case statement that's going to cause us problems, and the subject of the case statement is a signal called cell, which is a port here. This port is sized by a constant in the package that we're referring to with this use clause. So all of that seems standard VHDL code. How could anything possibly go wrong? So also have to remember that we need to obey the rules of the case statement, which are that when we say when, each choice must be unique, non-overlapping, and we must specify what happens for every possible value for cell. So we've definitely done that because we've got a when others clause, so we're capturing every possible value cell can have, and this ADDR control and status are not the same thing, they're not the same value, therefore they're unique. So there's nothing wrong with that, we may think, and when we go ahead and try to compile this, this is the error we would see. Expecting a locally static expression and so on, and it's pointing us to these when lines in there, so we think, why is this the problem? So if I was to try and very concisely describe what locally static means, it means for the design unit itself, so remember VHDL doesn't care about files, it cares about design units only, it needs to be clear from just the, in this case the primary and secondary design units, what size cell is, and it's not. It's not clear what size cell is because the definition of the size of this vector is held in a separate package. So although we're referring to that separate package, and of course this code would work in terms of visibility of what value APB address size has, this still doesn't meet the rules of what's deemed as being locally static. So to summarize what locally static means, it means you must be able to tell from the primary and secondary design unit what size cell is. That's the reason for this error. So that's really inconvenient. How do we work around this? One way, of course, and what many people do, because they don't bother investigating further, is just change this to a fixed number instead of referring to the package, which is extremely inconvenient and dangerous and not reusable. Or what simulators normally do is find a way around this. So this restriction actually went away in the 2008 LRM. So if you have a switch for compiling with the 2008 VHDL language reference manual, then you can use that, in which case the simulator should no longer give an error for that. Or, prior to the 2008 occurring, what would you have done then? Well, simulators supply switches. So in the case of the Cadence simulator, it's relaxing a particular check, and there's the mnemonic, and that's the mnemonic for locally static expressions in case statements in VHDL. So if I were to save this and go back now and recompile, the problem goes away. So I hope that explained any problems that you've seen in the past. These problems, you'd need to know where to look in the language reference manual, so you could read the whole language reference manual and still not be aware of why those specific coding examples cause problems. But hopefully that's given some insight now into the nuances of VHDL. Thanks for listening.